Hello! Welcome to one more lecture on this course of Fundamentals and Biomedical Applications of Quantum Science and Engineering. Well, last lecture we were discussing probability. And I give some examples. We define how is the probability, which is some event frequency divided by the total possibilities of my sample. And now I want to finish that part. And that was somehow discrete. Things happens like, is this or that, not in between, right? This is what we call discrete probability. And normally there are many possibilities because there are many events that you can take out of my sample, of my possibilities. So it comes that we create the concept of representing this as distribution of probabilities. And we're going to first speak about the probabilities that we saw already. We have a set of variables that normally we're going to say that the number of the variable is capital X. But there is a countable sequence of events, x1, x2, of distinct values for this variable. Because of course we are interested in quantifications of things, of properties and things. So suppose you have any variable, like this is quantity of rain, and then you can have it's not a good example of quantity of rain because it can be anything. But like the number that appears when I roll a dice. That's a quantity, and there are many values possible. When I have distinct variables, countable sequence, I call this a discrete probability, discrete sequence of events. Okay? So this is discrete. Different values and nothing between them. So, and in this case, the probability of the variable be any value is given by a specific number that we know how to calculate by their frequency divided by the sum of all possibilities. And we know that the sum of all the probability of all the events has to be unity. This is discrete. I have the distinct values and nothing between. I count them. I can count. They are countable sequence. 1, 2, 3, 4, 5, 6. Those are the numbers that can appear in a dice. We cannot have 4.5. That doesn't belong to here. 4.6, we cannot have it here. 3.2, we cannot have it here. So because they are countable, discrete, we call this discrete distribution. And then we normally represent, if we put the value and the probability, we can have different ways of presenting this, and this is called distribution. It's how the probability of some value depends on the value itself. This is called distribution. And for the discrete values, we have many possible distribution. So this is we call Bernoulli Distribution. I give you the name because it's very nice to know the names. You always impress people in a conversation when you know the name of these distributions. So this is what we're doing. This is like, suppose we have a set of two events, like flipping a coin or anything like. And then the probability of happens, one of the possibilities is theta. So theta is the value of the probability. And for the second possibility, of course, is 1 minus theta. Then when I represent P and X, now X can be only two things. This is what we call discrete distribution of probability. And there are many different distributions because depending on the behavior, right, of the probability with the event, with the variable, you may have a very interesting dependence on this. And there are very famous distributions that nature presents to us. So suppose here that there is one event that has one probability, theta, and the other is 1 minus theta, but they are not the same, right? This is it's not a regular coin, it's a vicious coin. It's a coin that was prepared to have more one thing than the other. Now, the question for probability, for distribution here is, if I repeat the experiment any times, what is the total probability of getting one of those? And then we can deduce this. We can construct all the possibilities. As I told you, you come with factorials and everything, and then we construct a distribution. It's like a function, but it's not a full function because it's discrete. N is a number, and x is also a value in this number. And then this distribution, if you flip any times and you have those two possibilities, that's what turns out to be the overall possibilities of getting one of the values, either x. It can be, it turns out that I ask you, what is the probability of having one of those events? And then, no, the question is, repeating any times, what is the probability of x times? So x also is a number of event 1, event that has the probability theta. Constructing this, we can get those nice distributions. This is called binomial distribution. It's very much used in many situations, including in bioeffects. Right? This is binomial distribution. And normally we can represent in a graphic those distributions, right? We put in a graphic, and normally they look beautiful like this when we put in a graphic. Depending on the value of theta and the number that I'm considering, the appearance will be, of course, remember, that's the probability of repeating any times, which is 20, the experiment, and what is the probability of appearing x times what I desire that has this probability, the event 1. It can be anything. Normally this can be put in a graphic like this. So depending on theta, depending on the number is fixed here, but varying the theta, which means the probability of that a single event happens in a single, in one of the repetition, right? In a single of those events happen, that varying the value, you see the distribution is moving. Originally, if theta is small, it is more closer to small values of x is the peak, and then decays away. Now, if we increase theta, we go to half, we get that. It goes, and it's very nice because it's half. You could imagine that peaks at the middle of the sequence, which is 10 event. I made it 20 repetition, and you know, because it's half, so the most probable appearance of whatever has this probability, which is head, or it turns to be half of it. You know, it's everything's logic. And there are many other distributions. Poisson distribution. Poisson distribution is very much used, geometric distribution and everything. Normally what changes from one distribution to the other is how is the behavior of px depending on the value of x. Now, this is when we use discrete, which means, you see, countable things, as the way we did. But most of the things can be continuously. As I said in the very beginning of last lecture, sometimes I want to ask what's the probability of rain tomorrow. But sometimes I want to ask what's the probability of rain 3 millimeters of water tomorrow, which is quantifying, right? 3, but could be 2.999, could be 2.5, could be 1, could be 1.6, could be anything. So this is continuous. It's not discrete. And in this case, it's a special case that we have to worry about. And then I'm gonna use the rest of this lecture, explain to you this continuous distribution of probability. You already understood what is distribution. Is when I do this full experiment with many times or many things, I want to construct how the probability is distributed depending on what I expected. So like I flipped 20 times the coin, and I want to know what is the chance that I will obtain 5 heads and so on, right? And that's what we gave there. Now here, it's different. The value can be anything, and then a new thing comes out of this that we have to understand. The first thing is understand what is a continuous variable in this distribution. In this, what is a way of dealing with a continuous event that vary continuously. You know, a variable that does not have a discrete value, something that can vary from in an interval, full interval, which characterize the things that we call continuous distribution. Well, first of all, we have to say what is this variable which is continuous. This is a uncountable, or I cannot count. So normally values goes in an interval. So I'm dealing with looking for possibilities of some event to take place, but the variable that I'm dealing with, it goes continuously in an interval. Right? So it does not make sense to speak about one value. It makes sense to speak about intervals, because it's continuously. Because there are infinite possible values. If there are infinite possible values, if I ask you for a continuous variable, that is something that can vary continuously in a sample, and I'm going to deal with the probability of an absolute value of that is 0. This is important of the continuous distributions or the distributions with continuous variables. We're going to see some example of continuous things. I already give you the quantity of rain is one of them. So if I ask the question, what is the probability of an absolute value, not an interval, is 0. Because I have infinite possibilities of absolute values. I am in an interval. In an interval of 2 values, can have infinite values because it's continuous. Can be anything. So it's 0. This is a very interesting characteristic that make a very big distinction between continuous, discrete variables and continuous variables for probability. So the probability to have an absolute value is 0 when we're dealing with continuous variables. So it doesn't make sense to ask that. Right? Doesn't make sense to ask. Normally you have to ask things in an interval. Okay. You already seen that when we're dealing with things that can vary continuously, not like the number in a dice or head and tail, we are dealing with something else that varies in between those things. Right? It's like an infinite faces dice. Can have any number. That's a complicated thing, right? Okay. In this case, is important and necessary to come with a new concept. And what is this new concept? Is the concept of density function, or density function of probability. And And I want to explain to you this concept. I want to explain what is density function or density of probability. It's only important when we're dealing with continuous variables, right? And because when we're dealing with continuous variable, the absolute value it's something that doesn't make sense for us. So we're going to deal with interval. And in mathematics, when dealing with intervals, we have to learn to integrate, to add up all things in an interval. But there are infinite values. It's not like a discrete sum. If it is a discrete sum, we are in the discrete probability distribution. Here is a continuous. Then to add up things, we have to come with the integral. And, you know, if I have a sample, if I'm dealing with some phenomena, that has a continuous variable, and that's mostly what we're going to use in quantum science, continuous variables. But there are some discrete too, so we're going to use both. But here, that's important because we'll be in the definition of things. Then once I created this function, which represents what is the probability per unit of a variable x. X can be anything here, space, but can be time, can be anything, right? Any quantity out of my sample. I'm doing things very generic, right? I'm creating the mathematical basis of this probability stuff. So we defined that the probability of this variable to be in an interval that goes from a to b is the integral of this function. This function is the density function. Density of what? Density of probability. The integral from a to b of this density dx, so whatever is the space I'm dealing with, is x. It's generalized. The integral from a to b of this density probability in this interval creates the probability of my variable to be in this interval. So now it's different, the concept. Because before I was dealing with discrete values. Now I'm dealing with a function. I'm dealing with a continuous distribution of values. And then this density function is essential, right? As I told you, this density function is density of probability. That's why adding up in tiny little intervals. And its density in this space, because multiplied by a variation of this space, give you the real probability stuff. So f of x is the probability per unitary value of this x space, which can be many things that we're going to define, right? So it's not only one thing, it can be many things. And this is like we are able to represent this function. Now it's a function because things are continuous. This is the variable, which can be anything we consider. This is the density function, and normally it has a kind of profile with some properties that we're going to see. And the probability of being between a and b in this interval is just the integral of this function. So the probability is just this. You know, the integral of the density function between 2 points is the real probability of making an observation. The value of x will be in this interval. That is the meaning of this. Okay, repeating. The integral between a and b is actually the probability of making an observation of my sample. This is still a sample S, but there is no discrete values for the events. They are continuous. It's a variable. And the probability that I make an observation or something happens and the value of this event being between A and B is exactly the integral under the density distribution. So you see, when we're dealing with continuous variables, we're going to deal with functions. Basically, this is my message. But those functions cannot be anything because we're dealing with probability. So we're going to have to find what are the properties of this function that represents also probability. Okay? So again, in my sample now, my variable can continuously vary. And I am asking, or I'm evaluating, what is the probability of this variable out of my sample to be in some interval of values. It's like it's going to rain. I want to know what's the probability to rain between 2 and 3 millimeters of water. This is a continuous thing. Exactly 3 is hard. Normally we get a put in it because there is a distribution. I hope you are starting to understand these things, moving from discrete. The concept of probability is the same, but the way the sample, the way that our universe of variables is present to us is different. Before we had the discrete things to happen. Now we have continuously things to happen. There are many, many examples around. This is, normally when we're dealing with the micro world, atoms, molecules, and things like this, so many things can happen because I have so many atoms and molecules, and the values of some properties they can acquire is so huge that they build up a continuous distribution of things. And this is important. This is what determines chemical reactions. This is what determines many things, as we're going to see. And the way to deal with this is to find out what is the density function, the density distribution of probability. Normally we call probability density, right? And what makes sense in evaluating the full probability in an interval is the integral. So now it's not like constructing the sample with the discrete possibilities. We're going to come up with a function. And this function will let us understand what is the probabilistic behavior of the system when it's observed. And that determines the probability of the system. Okay, so in doing that, in doing this distribution, now you see we have a function that represents the distribution of probability. So we don't speak anymore about values, discrete values. We speak about intervals. So it's better to know the function. We can construct any interval we want. In particular, when the interval b minus a of this variable is small, normally things that are small we call delta. When I do everybody knows that an integral, and this is close to this, is basically the value of the function times the interval. The interval is delta because now my integral goes from a to a plus delta, right? B is a plus delta. Therefore, this probability, which is this integral, is basically the value of the function is the value of the density probability distribution in that value times the interval. So this is almost transforming the continuous in almost discrete, but not quite, because you still needed the delta, which is small, it's true, but we need it. And when delta goes to 0, this goes to 0. That's why we said that in a continuous distribution, in a real continuous distribution, whatever you make absolute value, no, I want the probability of this value, a specific value here, it goes to 0 because the integral is 0. It's almost impossible in an infinite number of possibilities for that things to take place. That's why this goes to 0. And this is in here. Now, it's nice to know that when we're dealing with a small interval of many possibilities of intervals, then basically this transforms into a value that you don't even need to do the integral. You just take the function and multiply by the function in that value of the event, whatever is the quantity that we are putting here to quantify the probability. So it's the distribution at that point times the delta. So basically what we're doing is, when we want to make a delta that is small, basically the integral is this value, which we call delta, times the value of the integral in this point. This is a special point here, and the function we characterize f small f. So that put me in a situation to say that for a continuous values of probability, so if I have things that varies continuously, they are not discrete, what's matter is interval. What really is the right question to ask is, what's the probability of this variable or this quantity to be in an interval? That's what makes sense, and that's what makes things really possible to be calculated and everything. Okay, continuous distribution of probability is something that's, it's not very different. It's like we made this, if you divided this in little deltas, it's like discrete, but we don't know how to add up because it's too many elements, so we come with the integral. This is really important in here, because this actually is the probability. This is like summing all the possibility or the probabilities for the value of x to be between a and b in tiny little infinitesimal intervals. So this guy here is actually the probability of the value of x to be between x and x plus dx. This is what's the meaning of this guy here. Therefore, we have to create the concept of density of probability, or density function of probability. There are many names we give to the same concept, right? Density of probability, density function of probability, and so on. As I just said, because f of x dx is the probability of the value of this variable x to be in this interval x and x plus dx. When I add up everything, I am adding up all the possibilities of my sample. So the probability of the whole sample is the integral of this function over the whole universe of possibilities. And therefore, as we learn, if this is a probability, it must be U1, must be unit. So the integral, this is an important property. This is very important. The integral of a real density of probability has to be integrable, and the integral has to be 1. Right? So normally we say that these functions are normalized when the integral gives 1. And we find many ways of making those functions to add up to integral. Make up in a way that the integral is really unit. Well, we have many examples of this. I'm not going to give it all, but let me give you some. Like suppose we have a uniform distribution in a length of possibilities L. So I'm considering only from 0 to L. Whatever is the variable x here that we are considering. So whatever is the x that we are considering, it goes from 0 to L. And it is constant, so it's some value. What is this value? Easy. I know the integral of whatever I'm asking, which is constant. From 0 to L has to be 1. Therefore, the function has to be 1 divided by L. Right? Because this is the constant times L. So the constant, which is the value of the probability, is 1 over L. So this is a constant function and has the value 1 over L. This is very nice because sometimes, even though the density probability varies around, we consider a sub-interval of the possibilities of a variable x. And we know that's the inverse of this length that we consider is the distribution of probability, or the density of probability, right? If this is real space, you see that the probability has dimension of 1 over space. That's why multiply by space will be adimensional, will be with the dimension of probability. Now, if I ask for you the question, what is the probability of I make an observation of this distribution, whatever it is, and find something and find x in the interval AB, of course, it's only coming here, and A and B, and this part of the integral is the probability of this variable to be between A and B. And it is, of course, you can do this, is trivial. The area of this is B minus A times this height, which is 1 over L. So the probability of being in an interval is the interval divided by L. Right? For x belonging to this is the distribution. This is function of x. It's a constant, of course, but now there are also many distributions that exist around, which make sense and people use a lot. And you're gonna find many of these distributions. One of these distributions is called exponential distribution. What's going to vary now between systems, many systems we have, is how is the expression of the function, right? So the function can be many different things, and one of the things it can be, nature chose a few things to be like Gaussian, like exponential, and there are some explanations for that. And the probability distribution for some class of possible phenomena is exponential. And normally the exponential looks like this. For this variable bigger than 0, and for smaller than 0, we say 0, just to restrict the space. Otherwise, this is going to explode. And this has to be, the integral has to be 1. And this is how the function looks like, how the distribution function looks like. At 0, the function is lambda, and it goes down exponentially. Now, what is nice is that there is an explanation for this. If you ask, what is the probability of my variable to be above some values? I want my variable to be above x. What is the probability that I make an observation and a system that has this distribution? What is the probability of my variable to have a value above some x that I chose? So the integral, I put x prime just to distinguish between this x here. But it turns out that if your system has an exponential type of probability distribution, this is exponential, because I do the integral from x to infinite. And going from x to infinite, the integral is exponential. And that's a physical interpretation of this. As you go further up with the value of this, it goes down exponentially. And there are many phenomena in nature that obeys that kind of distribution. That's not the only one. There are many others, like Gaussian distribution. Oh, Gaussian appears everywhere, and there is a reason for that, you know. But Gaussian distribution, the function is a Gaussian. Of course, there is a definition of the width of the Gaussian, the center of the Gaussian, and that has to be normalized because the integral has to be 1, and therefore, you know, you have those coefficients here in front of it. Okay, and of course we can show that this is in the 0-1 interval. Okay, now when we calculating this, there is one thing that's important. Either if the probability is discrete or continuously, or continuous, we sometimes want to know the average value of some variable that is in the event. We want to know what is the average value. If I make an observation many times, what will be the average value? It's like rolling a dice, and then I ask, what is the average value that the dice shows? Of course, you may think it goes from 1 to 6. The average is not one of those numbers. The average value for a discrete distribution is just the sum of the possibilities times the probability of each possibility. If I add up all this, I get the average value. This is what we call the weight for each value. The probability of each value to happen is its weight. And the weight times the value give the contribution to the overall value after many observations. And the average value, like rolling a dice, we know that's 1/6 of each value, and the values are 1, 2, 3, 4, 5, 6, each with the probability 1/6, and therefore give you 3.5. You know, the average is neither of the values that shows in the dice. You know, average is very important because either for discrete or continuous distribution. When I have a continuous distribution, I calculate sum, making a sum of the values and the probabilities the way we define here. This definition is important and we're going to use a lot, so please keep it in mind. What is the average values? And then there are other definitions, deviations from average and things like this that will come in the future as we need. But this is important, calculating the average. And then there is another thing which is calculating the average when we have a continuous distribution. If we have a continuous distribution, we told that the value x appears with a probability that's f of x dx. But instead of sum, I'm going to integrate in the whole space, in the whole sample. And the average value of some continuous variable is the integral of the variable times the density function. This is how I calculate the average value for a continuous distribution. Okay, to illustrate, so you see, this is also important because it's a way to weight. So I give a weight of the probability for that value to be, multiply and add up, and I get the average value. I'm going to give you an example, an important example of continuous probability. Is the velocity distribution of atoms and molecules in a gas, or it happens also in liquids and things like this. We all know that if I have a container and I have the molecules inside this container, I have some number of molecules n, and they are confined in a volume v. We know that due to the motion of those molecules, there is a pressure, which is the momentum transferred to the walls, occupying the volume. And this movement, the kinetic energy, characterizes the temperature, and there is this Boltzmann constant here. K here is just the Boltzmann constant. So Boltzmann constant is here, the total number of particles. But this is a macroscopic observation. This is consequence of a distribution of velocities. And this distribution of velocity was very important in science. And people were able to measure this velocity distribution using special techniques like we use that spin around and make the molecules to pass through, make a beam of molecules and measure. Many people did that. And if they look in intervals of velocity, they found that the number of particles or molecules in your sample obeys, depending on the interval you're looking, you found more and more and then less and less. That is a distribution. They divide in intervals. Normally we divide in intervals to measure. But it's so many molecules and the velocity can be anything. So it's a continuous distribution. And now we're going to ask the following question. What is the probability to find one molecule within a special interval of velocity? And that's the question that we are asking. And we can deduce that based on probability distribution and everything. And Maxwell, the great Maxwell from Maxwell equations. And Boltzmann, the great Boltzmann from statistical mechanics and everything. They calculate what is this density, which is probability. So the probability, the density probability for the velocities of atoms or molecules in a gas is given by this function, which is called the Maxwell-Boltzmann distribution, right? This is the distribution. So it is the distribution of molecules with respect to their velocity within an interval. If I ask you what is the probability to find an atom in this sample, I go and measure what is the probability to get an atom with velocity between v and v minus dv. So that probability is f of v dv. Exactly the way I explained to you the concept of continuous distribution of molecules, right? And the integral of this distribution is 1. Of course, it's probability, right? It has to be 1. You can do the integral. It's depending on the temperature, which is a macroscopic property. This gas is in some temperature T. And that's dependent on the temperature. And m is the mass of the molecule. So I said here, but I did not mention clearly, that we are dealing with particles with mass m and they are in a temperature T. In fact, they use this distribution for the definition of temperature. The definition of temperature obeys this kind of thing in most parts of the system. If I look at this function, which is the distribution of finding a molecule with some velocity when the gas is in some temperature, is given by this. It's a very nice distribution which grows up parabolically for small v and then turns out has a maximum value and then die out in a quadratic exponential, right, with velocity. If I move the temperature away, if I increase the temperature, this displaces to higher velocities, of course, because higher temperature, as we know, means higher velocity of the sample. And then from the distribution, we can come and calculate many things, like the most probable value of the distribution, which is the maximum. And the way we do that is easy. To obtain this, we see where this turns around, where the derivative is 0. And it turns out that if we do that, the most probable value is root square of 2kT, Boltzmann constant, temperature divided by the mass. This is the most probable. Now, what is very, very interesting is what is the average value of the velocity. And then we have to do the integral from 0 to infinite, because the velocity, we are dealing with the modulus of the velocity here. Only the absolute value of the velocity. So the integral of f of v dv. You see that the variable here, x, that I proposed in the very beginning, now is velocity. X is a generic variable, can be anything. It's exactly 1.12 times root square of 2kt. If I apply this for the air, so if we take air, which we know the most important component of air is nitrogen, and we apply this, we get about 500 meters per second of velocity. Wow! Molecules in the air are really moving fast because the average velocity is 500 meters per second, right? And this is really amazing. And this is why we have an atmosphere at environmental temperature, because they have so high velocity. If they were very low in velocity, they would be very close to the ground. But they have a high velocity. They can go up, fly apart, and we can prove that's called gravimetric or barometric, distribution of gas because of the gravity and everything. Okay? But, and then they make this nice atmosphere. This is a very interesting distribution. And if I ask you how many particles is in an interval, right? Because I told you the idea to have a continuous distribution is to be able to investigate intervals of variables. And the number of particles in some interval between V1 and V2 is n, which is the total times the probability of having particles in that interval, which is the integral from V1 to V2 f of v dv. Right? So the probability, that's the number. The probability is the number, is this event, which is the frequency that happens, which means how many particles are in that interval, divided by the total number, and this turns out to be only the integral. The integral between that interval is the probability of the velocity to be found in that interval. You know, continuous probabilities everywhere, and will be also in the quantum mechanics. So with this lecture, I finish the revision of all the concepts I want to give you. The importance of quantum mechanics, the revision of waves, and now the revision of probability. Now that we are prepared, next lecture we're going really to start to go into the concepts, how science found the quantum mechanics, how they develop all the equations, how they develop the concepts they need. See you next lecture. Bye-bye.